Greetings and welcome. We've been talking about linear functions. We are continuing our look at the linearest of functions, the liniest of them. It says a solution of a linear equation in two variables is an ordered pair x comma y that makes the equation true. So remember, we talked about linear equations can be written of the form y equals mx plus b, where m and b would be like some numbers. So for instance, what if it was like y equals 3x plus 2? And they're saying a solution of a linear equation, Ethan, is going to be any combination of x and y that make this true. Okay? Any combination that makes this true. All right, so for instance, if y was 5, what do you guys think x would have had to be? If y was 5, 3 times what plus 2 is 5? Let's see, 3 times 1 plus 2, right? 3 times 1 is 3, plus 2 is 5. So 1 comma 5 would be like a solution of that linear equation. But that's not the only solution, right? We've been used to problems where sometimes algebraically it'll have a solution, x equals 2. But lines are going to have lots of solutions, lots of combinations of x and y that make that equation true. That doesn't mean anything's true, okay? It just means that there are infinitely many things that work and infinitely many things that won't work. So here we go. In terms of functions, there's another way to classify them in terms of domain as discrete and continuous. Okay? And you guys can probably tell just visually looking at these two examples, Cameron, that discrete functions jump, they teleport, right? They warp, and they don't exist everywhere in between my points. All right, so a discrete domain is a set of input values that consists of only certain numbers on an interval. So like integers from 1 to 5 are the counting numbers that wouldn't include fractions or decimals. So this would be discrete, whereas continuous is everything between there. All right, infinitely many solutions, right? 1.1 works, 2.718, the square root of 2, which is a roughly 1.414, infinitely long, non-repeating decimal, would work in this case. And everything in between would be continuous. The way I remember continuous is that if you were to draw this, right? If you were to draw this, I could put my writing utensils down and continuously draw until I'm done. Whereas if I tried to draw this without picking up my writing utensil, I can't. I'm already drawing way more points than I need, right? The only way I could draw this is to kind of like plot, skip, plot. And so that is not able to be continuously drawn. Yes. So let's do an example. Example 4. All right, so Devin's checking his phone. You won't find example 4 on your phone unless you were checking my awesome Google Docs, in which you probably have access to this. But I doubt that's the case. So let's see, example 4, I happen to already give us a nice little graph to work with, a grid, so you're welcome. Kind of set us up for success. And it says this: a linear function y equals 15.95x represents the cost y in dollars of x tickets for a museum. Each customer can buy a maximum of 4 tickets. It says find the domain of the function. All right, so we'll eventually graph this, but for part A, to find the domain, the question I would have for you is, can I buy 0 tickets? Yeah, 0 is a number of tickets that I can buy. Can I buy 1 ticket? Yeah. Could I buy half a ticket? No, like museum's going to be like, what does that even mean? Dude, you're a whole person, right? Doesn't matter. You count as a whole person. You pay the full price. And so I can't have values between 0 and 1. I can only buy these counting numbers, these whole numbers. I can't buy a negative number of tickets. That would be like if I was scalping tickets and but giving them to the museum, and they're paying me to keep their ticket. That doesn't even make sense, right? That's not how the museum works. Also, sometimes I say museum like it's spelled with a Z, but it's really a museum, right? Because you go to the museum to see them all the stuff that they've got, right? I'm going to go see them dinosaurs at the museum, right? And that's what you would do, right? So that's how I remember how to spell it, but I still don't pronounce it. I say museum. All right. You could buy 3 tickets, and then it says maximum of 4. Does that include 4 or everything less than 4? That includes 4. I agree. So this would be the domain. And then they ask the question, is this discrete or continuous? Let's see. This will be discrete, because it doesn't include everything in between 1 and 2, or 2 and 3, or 3 and 4, right? It jumps, you could say, right? I'll just say, yeah, it doesn't include anything between those points. Yeah. Although it is possible to have a discrete function that would be like the list 1.5, 2.5, 3.5. That's a discrete list. In this case, the whole numbers were the only ones that worked, but I just want to point out you could have those other ones. Let's see. So let's find out what the graph would look like. So I'm going to make a table here, and this is a calculator question because I saw some decimals, and I'm not the best at all of the decimals. So I'm going to make a table. I've got my function y equals what, 15.95x? Was that what it was? Or was it 1495? Awesome. And here's y. And so I've got possible inputs are 0, 1, 2, 3, and 4. And I'm reaching for my calculator here, although you probably can already tell me, what do 0 tickets cost? 0, right? Like the bank can't be like, hey, you need to pay us for your tickets that you didn't buy. Like that, I'd be like, that's a no-go, friendo. I don't think so. How many does 1 ticket cost? How many? $15.95. All right, let's plot some of these points. So at 0, if this is tix, T-I-X, and this is my cost measured in dollars. Let's see, dollar, swoop. 0 was 0, so I'm going to plot the point 0, 0. Maybe I made yours wider. Yours is probably better. My bad. 1 is going to cost $15.95. On my graph, this was 20, right? Half of 20 is 10. Halfway between there would be 15. So I'm going to go over 1 and up just a little bit past my 15 mark. Okay? So it's an estimate. It's not perfect. Let's see. What's $15.95 times 2? I got, my calculator says 31.9. Yeah. But we could call that 3190. Yeah, I think that makes more sense. So let's see. So here's 30. So over 2 up to 31.9. It's going to be closer to 30 than it is to 35. So I'm gonna put that like right about there. Seems reasonable. Let's see. 15.95 times 3. Yeah. So over 3 and then up, here's 40, here's 50, here's 45. Right, so I kind of have to fill in the gaps or at least know what those tick marks mean. So let's see, 47.85, so that's going to be almost just a little past the halfway point, I think, between 45 and 50. And then lastly, multiply by 4, what'd you get? 63.80. All right, so over 4, up, looks like I might need to go a little bit past this, 63.80. And so, although these are line E, right, these all land on a line, it only exists at these points because I can't buy 1.5 tickets even though I might be able to predict roughly what 1.5 tickets would cost. Maybe it's around like $25 or something. I don't know. Right? But that would be the solution of this problem, right? That would be what the graph looks like. All right, let's jump to example 5. Here we go. Example 5, talking about calories. Gonna eat some food, some cereal bars. I think I have a cereal bar in my lunch today. Like in my lunch that is yet to be eaten. Yes. You already, or wait for him to come back? All right. Yeah, so I kind of obviously gave us a graph with lots of space, right? And I kind of pre-sized the graph, but eventually you'll want to have a rough idea of how large you need to go and how far over you need to go. And you could kind of estimate that based on the equation. But it says a cereal bar contains 130 calories. The number C calories consumed is a function of the number of B bars eaten. Does this situation represent a linear function? Yeah, it's got a constant rate of change, right? For every 1 bar, we get 130 calories. And that's a constant rate of change, so this is linear, right? It's constant. Constant rate of change. The function isn't constant, its rate of change is constant. I'm being specific there. Yeah, some of our homework's going to be like this. Find the domain of the function. All right, how many cereal bars can I eat? I don't know. How depressed am I? Who knows? Let's see. Can I eat negative cereal bars? Not unless they were yesterday's cereal bars and I was feeling nauseous. We'll say 0 is the first number of cereal bars I can eat. Now, technically, I can eat half a cereal bar or a third of a cereal bar, but based on this problem, they're just going to have us count by whole cereal bars. As if, like, you don't know how to take a bite. You literally just, like, slide the cereal bar into your mouth and swallow it whole. I don't know. It'd be weird. It'd be weird, yeah. You're right. It doesn't give us a maximum number of cereal bars. And it seems like it would be a list, something like this. And I put ... because I think that you could just keep eating, man. Yeah, I guess, yeah, at some point, there's a finite number of cereal bars that could be consumed by a single human in the average lifespan. Yeah, man, that doesn't sound like the life for me. I don't think I want to just be force-fed cereal bars forever. Now, question, there's infinitely many numbers in this list that I've made. Maybe your list, maybe you could argue it's less than infinity, but... is this discrete or continuous? Yeah, it's going to be discrete, because they didn't let us include half cereal bars. All right. So they didn't let us include things in between there. And then they ask us to, let's graph it, friends. Right, so our solutions are going to be combinations of x and y that would make our equation true. Now, we actually haven't even made an equation yet. Maybe we could predict the equation. When x is 0, the number of calories I get is 0. When I eat 1 cereal bar, I get 130 calories. When I get 2 cereal bars, how many calories do you think I'm going to have? 260. And this is a constant rate of change. It's 130 per 1. So my equation, I think, is going to be 130 multiplied by x. And you know what I realized? I already changed the name. They already gave me C and B. That's my bad. We'll be fine. We'll live with it. All right, so So maybe I could pretend this is my number of bars eaten, and this is the number of calories consumed. All right, so my equation is just going to be 130 times x. So let's find some more. We'll go out to 4 maybe, and then we'll predict the rest. Okay, so Cameron, 0 times 130 was 0. 1 times 130 was 130. This was just increasing by 130 each time. Because I knew this was linear, I actually could avoid doing some of the work. So 3 times 130 is 390. Yeah, and I could have gotten that by doing the workout or by using my pattern. And let's see, this one's a little trickier. 4 times 130, what do you guys think? I think it's, yeah, 520 is what I'm feeling. So let's plot some points. So 0, 0, right there. 1, 130. That's going to be about here. Somewhere between 100 and 200, and I put it closer to 100 because it's not halfway between those. Then we've got 2 and 260, so that's going to be more than halfway between. Right, here's 300. And then 3 and 390. That's almost at the 400. And actually, you can see this is forming a line for my pattern here. And it's actually, graphically, it's going up 130 over 1. Up 130 over 1. Up 130 over 1. And it continues as such. And so 4 is going to be at 520. Something like that. And if I wanted, I could actually continue to predict, maybe, according to this pattern. Watch this. Now, this is... the points in between didn't count, so I'm just lightly drawing this line here. Right? They weren't allowing us to eat half a cereal bar, but I just want to point out that I could then kind of predict, like, okay, it looks like I'd have somewhere around, I don't know, 660 if I eat 5, and it looks like I'd have somewhere around almost 800 if I eat 6. And it looks like I could use that to kind of predict some other points, even though it's a discrete function. That's what I would end up having. All right. So the solutions of this function end up being, right, these sorts of, they can be represented by graphs, they can be represented by tables, and even though this one has infinitely many solutions, I can at least get an idea of what it looks like. Let's see, this is tricky. This is backwards now. What sort of situation would be continuous versus what sort of situation would be discrete? Could you make something up for either? Yeah, what do you think? Well, this one's making jumps, so this is discrete. But they're actually asking us to make up a story that would describe this. Yeah, like what's a real life situation that could be described by that? Let's see, number of math problems done. Or maybe math problems left, I guess, over time. Something with swimming. Okay, like distance over time. Maybe distance to edge of pool. And x could be time. Now this one kind of almost works, except this would have ended up being more of like the step function that we saw earlier with the eggs, based on the way that I've worded it. But yeah, some situations, usually things related to counting, are going to be discrete, right? Things that don't have half amounts is what's going to be discrete. All right, so thanks for watching, Internet friends. Have a good day.